Jump right in. Hey there, Chemistry 3101. We're going to start up with Chapter 8 now, which deals with addition reactions of alkenes. So you can almost refer to it as the alkenes chapter. That's what we're going to focus on in this chapter. And if we start off, it says here, Section 8.1, Introduction to what an addition reaction is, and what are some of the common types, of addition reactions. Well, we covered elimination, and elimination is when you lost atoms from a molecule to make a double bond, but now we're going to do the opposite. We're going to take an alkene and we're going to add two atoms or two groups to it. And so you see here we get the double bond breaking and we form two new sigma bonds here. So that's an addition reaction. And if you're wondering, well, what could X and Y be? That's a great question, okay? And that's covered in table 8.1. It could be what we call a hydrohalogenation reaction, where we add a hydrogen and chlorine, bromine, or iodine. So that would mean that you either add HCl, HBr, or HI. We don't do this reaction with HF. Okay, so we don't do hydrofluorination. We do hydrochlorination, hydrobromination, or hydroiodination. So we're going to cover that later on today. You can add a hydrogen and a hydroxyl. And if you're looking at these two groups and saying, well, together they make water, yeah, they do. And so we call that a hydration reaction, where you add H2O to a molecule. But again, you can think of the water molecule as being H and OH. So this is one group and this is the other group. So we're going to cover hydration in detail. Then hydrogenation. And in hydrogenation, what you're adding to the molecule is just hydrogen gas. Okay, so two atoms of hydrogen are what you're adding, hydrogen and hydrogen. What else is covered? We cover something called halogenation, which can be done with chlorine or bromine. So I really mean that. It means Cl2 gas or bromine, okay? And in that case, you add two chlorines or two bromines in a halogenation. And again, chlorination or bromination. We don't cover fluorination, and there's a good reason for that. And we don't cover iodination, and there's a good reason for that too. We'll get into that later. If you treat an alkene with a halogen, meaning chlorine, bromine, or iodine, and you put it in water, you do what's called a halohydrin formation reaction. So that means you add a hydroxyl on one side and a halogen on the other. And we're going to go over that in detail, halohydrin formation. And the last one is dihydroxylation. And you see that that's covered in two sections. And the reason why it's covered in two sections is because we learned cis dihydroxylation. So that means you put a hydroxyl on both carbons of what was the sp2 hybridized carbons previously. We learned how to do it in a cis fashion and a trans fashion, or what we call anti-addition and syn addition. And I'll get into more detail on that later. But again, we need two sections to cover dihydroxylation. So there's a whole bunch of different reactions that we learn and that you do need to memorize. Now, if you're wondering, do I have to know the mechanism for each one of these reactions? The answer is some yes, some no. And I'll go over those in detail, which ones you need to know. Now, if you look at the total number of slides in this slide deck, there's over 100. And once you get to the very end of the chapter, so let me just show you here. There's something here. Sometimes my students call this the wheel of reactions, right? Because it's kind of a circle like this. But this is where we're going in this chapter, is we're heading towards this, and we're going to look at all of these different reactions, okay? Every single one of these reactions in detail. Again, you don't need to know the mechanisms of all of them, but you need to know the mechanisms of several of them, and I'll cover that in detail with you. But if sometimes students will ask me, Mr. Dion, do you have a summary of the chapter? I'd say this is a pretty dang good summary of all the reactions that we learn. Now, obviously, if there's over 100 slides, we go into some detail on all of these reactions, and we have to consider things like regioselectivity, et cetera. Yeah, I think it would be a great idea to print this slide maybe and put it somewhere important and practice these reactions over and over and over. Very, very important slide. And if you go on the previous slide or the slide before that, it covers the names of all of those reactions. And of course, I'm going to refer to these time and time again throughout the chapter. So before we get into that, though, we've got to cover a little background on alkenes and a little bit of nomenclature. But again, why do we have a whole chapter focusing just on alkene chemistry? It's kind of answered here in a way. It says the pi bond, and you know that a pi bond is weaker than a sigma bond. Well, a pi bond can function as an electron pair donor. So what does that mean? it means there's two possibilities, right? It can either function as a base, right? If you think of a Lewis acid as an electron acceptor, a Lewis base is an electron donor, right? And then a nucleophile, well, we know that a nucleophile is a nucleus lover, so a pair of electrons can attack a powerful or an electrophile. So again, the pi bond, weaker than a sigma bond, can function as a base or as a nucleophile. And that is, in a way, why we need an entire chapter to talk about alkenes. Also, if you've ever wondered, sat there in class and just wondered, why am I studying this? What's the relevance of all of this? Well, the relevance of alkenes is that they're found in many, many naturally occurring compounds. And you see just a few of them here. We have this really interesting compound called allicin, which is responsible for the odor of garlic. And you can see there's two alkenes in it. We get a double bond over here, another double bond between two carbons here. Geraniol, which is kind of a polarizing compound. Some people really like the odor of geraniums, other people not as much. But you see that there's two double bonds in there, right? We have an alkene here, and then we have an alkene here. Now, something that you might notice about the name is that the suffix is actually -ol, which denotes an alcohol. And we have an alcohol here in the geraniol. And the reason why the compound is named after an alcohol and not an alkene is based off of something called the order of precedence of functional groups, and alcohol is higher on the order of precedence than an alkene. I'll talk more about that later on in the course. Then if you've ever noticed the waxy coating on apple skins, that's due to this compound here, which is alpha-farnesene, and you can see that's got a whole bunch of double bonds in it. The book goes on to a whole bunch of compounds here. This one is near and dear to my heart, limonene, which has two double bonds in it. It's responsible for the smell of oranges. It's a very inexpensive compound too. You can buy it by the liter for not very much. And when I was a graduate student a long, long time ago, the major part of my thesis was doing the synthesis, and my starting material was actually a limonene stereoisomer, which I won't go into the details on that. Alpha-pinene, which is found in turpentine, which is a paint thinner. Then you see cholesterol here. Cholesterol is obviously an alcohol because it has a hydroxyl on it, but cholesterol has a double bond in it, so it's got an alkene in it. Anyhow, there's a whole bunch of other compounds. I'm not going to go into all these. I'll leave this as kind of an FYI if you want to spend some time reading about more naturally occurring compounds with double bonds in them, or carbon-carbon double bonds. But another thing that my students have asked me, from time to time is, where do all these starting materials come from? Where do these ketones and these alkanes and these alkenes and aldehydes, where do they come from? Well, the answer is a lot of the organic compounds that we look at come from the petroleum industry. And I'm sure you've all watched the news and heard about the price of, a barrel of crude oil. Well, we know that we can only get a certain percentage of gasoline from crude oil, which is the major purpose for extracting oil. But we can get a plethora of other compounds from petroleum as well. And ethylene and propylene are two examples of alkenes that we get from the petroleum industry. And these are the starting materials, which we just use the fancy word precursor, it just means reactants, for making all kinds of compounds, not just propylene and, acetone and things like that. If you look over here, you can see that from the petroleum industry, we make all kinds of interesting compounds, right? If you're thinking, well, you can only get ethanol from a naturally occurring substance like corn, right? From fermentation process. That's not true at all, right? You can make ethanol from ethylene, and that comes from the petroleum industry. You can make ethylene oxide, acetaldehyde. You see, you can even make acetic acid, which is the major component of vinegar, vinyl chloride, and then you can convert that into polyvinyl chloride. And I'm sure that somebody who's hearing the sound of my voice has purchased a PVC pipe at Home Depot or something for a plumbing project. Also, ethylene glycol, which is one of the major components found in antifreeze, and it can also be used to poison a loved one if you want to. If you ever watch the Forensic Files, there's always a story about somebody, murdering somebody using ethylene glycol because, again, it's found in antifreeze, but it has a sweet taste. Don't worry, though. The ethylene glycol that's sold nowadays has been doped with a bittering agent so that pets and children won't get into it. Also, propylene. So propylene is an interesting compound. It can be used to make polypropylene. And me coming from the eastern side of Canada, all the fishermen use polypropylene ropes nowadays, which are pretty amazing. And then you can also get acetone, right? And acetone is the major component or is basically what nail polish remover is. And then propylene glycol is also found in antifreeze. It also has a sweet taste and is poisonous. Anyhow, there you go. So a lot of the starting materials that we see in organic chemistry come from the petroleum industry. Now we're going to move on into alkene nomenclature. So we haven't talked about nomenclature since chapter 4, really. In chapter 4, I taught you the nomenclature of alkanes. And a lot of what you learned in the section on alkane, so that was chapter 4, right? We covered alkane nomenclature. All those things that you learned in that chapter are going to be useful here because it's basically using the same procedure, just with a couple of modifications, right? We just tweak it a little tiny bit to name an alkene. That's all there is to it. So the first difference is this. When we were naming an alkane, all we had to do was find the longest carbon chain. Remember that? We just found the longest carbon chain by trial and error. Well, now we're going to up the ante. We're going to find the longest carbon chain, but it's got to contain the double bond. Okay, so it's got to be the longest carbon chain that has the double bond in it. And I'll show you an example of that in just a second. Then you're going to identify and name the substituents. Those are methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl, chloro, fluoro, bromo, iodo. I think those are the only substituents we looked at in this class. Then you're going to provide a locant. And remember, a locant is just a TSATSI word for a number, okay, and a prefix, di, tri, whatever, to each substituent. And you're going to give the carbon-carbon double bond the lowest number possible. I'll show you an example of that once we look at some practice problems here. And then you put the substituents before the parent in alphabetical order. We ignore the prefixes iso, cyclo, and neo when you're ordering it alphabetically. And then the double bond locant, so the number for the double bond can be put before the parent name or just before the -ene suffix. And again, you have to see an example of that to understand it. So I'll show you that in a few seconds. So let's take a look at some examples. Again, going back to chapter 4, when you named an alkane, what did you have to do? Just find the longest carbon chain and name it, right? Pentane. And so if we have a 5-carbon compound, it's the only chain to consider here, and it's got a double bond on it, we, instead of being pentane, we change the suffix to -ene. So it's pentene. And if you're wondering about the locant, remember the rule said to number the compound in such a way that you give the carbon-carbon double bond the lowest possible number. So you would start numbering over here, 1, 2, 3, 4, 5. Now the double bond itself can only be given one number, and so you give it the lowest number. So the name of this compound would actually be 1-pentene. All right. If you look at the compounds below on the bottom left, you see the longest chain is octane. Okay. But now if you put a double bond up here, the longest chain that contains the double bond is heptene. And so we would number that again, giving the double bond the lowest possible numbers. Okay, so the actual name of this compound would be 3-propyl 1-heptene. 1-heptene. Now you probably noticed that there was a rule here where it said you can put the double bond locant, which is its number, before the name or just before the -ene suffix. You could call this compound 3-propyl 1-heptene, or you could call it 3-propyl hept 1-ene. Either one is acceptable, okay? 3-propyl 1-heptene or 3-propyl hept 1-ene. I'll just tell you, I mean, I've taught this class a long time. My students usually lean this direction, okay? And there's nothing wrong with that. There's nothing wrong with either one. And I think the book leans towards this direction too. We'll use both, just to get some practice on it. Give me a thumbs up if you're with me on the idea so far. Because if you understand this, and of course, when I say give me a thumbs up, it doesn't mean don't ask me a question. Of course, if you have a question, please do stop me and say, hey, what the heck's going on here? Then we identify, name the substituent. So you have to know the same old alkyl and halo groups, assign a locant to each one of those, give the double bond the lowest possible number. And so you can see, correct versus incorrect, right? If you gave the double bond, this would be a 2-heptene, a 2-heptene versus a 5-heptene, right? 2 is lower than 5. And so if we were trying to name this compound here, so this is a 2-heptene, and then we have methyl groups at 5, 5, and 6. So you would call this compound 5, 5, 6 trimethyl 2-heptene. And if you're cheeky and you say, well, I called it 5,5,6-trimethylheptene, that's fine too, okay? They're both perfectly acceptable according to IUPAC. It's very rare that students ask me, why do you have both of those? Okay, and the answer is, it becomes more abundantly clear when you look at compounds that have multiple functional groups. Did anybody think of, something that we might be missing in this compound? Because there's one more thing that we're missing, and that's the double bond. We have to say whether it's cis or trans or E or Z. Could anybody tell me the double bond in this compound, would it be cis or trans? And this question is not designed to fool anybody. Yeah, thanks, Hannah. It's trans. So Hannah, you would call this compound trans 5,5,6-trimethyl-2-heptene. Also, let's try another one. Could anybody tell me, is this compound an E compound or a Z compound? And again, it's not a trick question. Would it be E or Z? Right, because you could label it as trans, yes, but you could also label it as E or a Z. Both are acceptable in this particular case anyway. Would this be an E? Yeah, exactly. It's an E compound. So if you were practicing this at home and you called it E 5,5,6-trimethyl-2-heptene, that's totally acceptable as well, right? It's E, right? The major group is here and then here, and those are entgegen or opposite to each other. Yes. So somebody asked me a question about the double bond. Does the double bond always get the lowest number? Yes. Forget about all the other substituents. Always go by the functional group. You give the functional group the lowest possible number. The other substituents be damned. Okay, they get whatever number is coming to them. All right. Okay, good. Well, I was pretty harsh about that. Really rough on those substituents. Anyhow, so you see the example here. We just went ahead and named it. Again, you could call it trans. Okay, 5,5,6-trimethylheptene or 2-heptene. Either one is fine. And then we put the E in parentheses. And that's something I don't pick on my students about. I'd say the homework might be picky on that. The homework can be a little testy sometimes. But there you go. All right, so those are the rules for naming an alkene. Now let's give it the old college try here. And students usually are very good at naming alkenes and alkanes and stuff like that. Look, let's start with this compound here. So this is 8.1a. I'll start out with a question that's a bit of a brain bender here on a Monday morning. Can this compound have a cis or trans, or E or Z? Or is this compound cis or trans? Oh, yes, it can, okay? So we have two different substituents on this carbon, and then we have two different substituents here. So could anybody tell me, is this compound cis or trans? I'll tell you, it's one or the other. It's either cis or it's a trans compound, right? But it's because you have an ethyl group here, and that's trans to this ethyl group over here. So you could call this a trans compound. Okay, so the compound is definitely trans, so we'll worry about that in a second. Now, I could start numbering over here, 1, 2, 3, 4, 5, 6. So that would be a 3-hexene, or I could start numbering over here, 1, 2, 3, 4, 5, 6. So which way is the correct numbering, do you think? The numbering in red or the numbering in blue? Either way, you get a 3-hexene. Well, let's think about that. So either way, you get a 3-hexene. Which way gives the methyl group the lowest number? Right, because that's going to be the tiebreaker. It's going to be the red one, right? Exactly. So if we'll erase all the blue here, there we go. So now we get a 3-methyl 3-hexene, and it's trans. So let's put this here. We'll put trans 3-methyl 3-hexene. Okay. Now, is this compound E or Z? Could anybody tell me? Is this an E compound or a Z compound? Again, it's not a trick question. Yes, exactly. It's an E compound. And so you could also call this compound E 3-methyl 3-hexene. Yes, there you go. All right, why is it E? Because you have this group, which is the major group on this carbon, and then you have this group, which is the major group on this carbon, and they're opposite or opposite of each other. Okay, so it's an E compound. Somebody just asked me an interesting question in the chat, okay, which I'm going to try to explain to you. Okay, somebody said, could a compound ever be cis and trans but not be E and Z? And the answer is no. If you have a compound that is cis or trans, it has to be either E or Z. Okay, any compound that's cis, any compound that's trans can be labeled as E or Z. However, the reverse is not true. If we have a compound like this compound here, this compound has to be either E or Z, but this compound cannot be cis or trans, because the only time we can apply cis or trans is when we have two groups that are identical. This is an ethyl, this is an ethyl. So we can use cis and trans. But if we go to this compound in B, here we have something, this is a 5-carbon group. Here we have an ethyl. Here we have an isobutyl. And oh shit, here we have another ethyl. Oh, damn it, I was wrong. Okay, so I guess this one can be trans. So this is a trans compound. But you can have a compound, like let's say you had a compound like this, okay, where you have a chlorine and a tert-butyl, and let's say you have an ethyl group here and a proton here. Well, this compound cannot be cis or trans. It's impossible because you don't have two groups that are the same. But can it be E or Z? Yes, it has to be, right? This would be a Z compound because the chlorine and the ethyl group take precedence. Does that make sense to anybody? Okay, cool. All right, good. Anyhow, I'll erase this stuff, get it off the screen here. But anyhow, there you go. It's a little short explanation. Well, Savannah, where was I? So is this compound a cis compound or a trans compound? Anybody? And anybody get that? Yeah, it's a trans compound. Yeah. So this compound is trans, right? Because these two ethyl groups are trans to each other. Would it be an E or a Z compound? Yes, it's an E compound, right? Because you have this group which takes precedence here and this group which takes precedence here. So either one, it's trans or E. You can use either one. I don't even know what the solutions manual uses, but let's take a look at it. Let me just erase some of the spinach here. So we want to find the longest carbon chain that contains the double bond, but the one that has the most branches. We want to have the one that has the most branches on it. And so that one, I've already found it. It's this one here. So if you go 1, 2, 3, now maybe I could trace it with my yellow pen. Try that. So it's going to be there, here, 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 and here. Okay. Now, should I start numbering from where I have this red circle or from where I have this blue circle? Could anybody answer that? Yes, from where the red one is, right? Because then you'd have 2, 2 instead of just a 2. Yep, good. So let me just erase that spinach. And we'll number here. We've got 1, 2, 3, 4, 5, 6, 7, 8. So this is a 4-octene. So you could scribble that down if you wanted to. Let's make a list here. There's so many groups. So this is some kind of 4-octene. Then we've got a 2,2,7 trimethyl. So 2,2,7 trimethyl. What else do we have on here? We've got a 4,5 diethyl. So 4,5 diethyl. And I think that's everything. So now we're going to put it all in order. And so when we put this together in a big nomenclature sandwich, we get trans 4,5 diethyl 2,2,7 trimethyl. And then 4-octene. All right. Or we could call it, I'll just copy and paste this because I'm too lazy to write it all out again. Work smarter, not harder, right? So copy, paste this over here. There we go. And you could call it, oops, we'll put that in black. There we go. You could also call it E. 4,5 diethyl 2,2,7 trimethyl 4-octene. Is that a long enough name for you? Okay. Everybody kind of with me, even, 70% of the way on the rules? Cha? All right. Cool. Are you going to have to try it yourself? Absolutely. Yes. Everybody has to practice nomenclature. It's a big part of organic chemistry. Yeah, it's not uncommon for a seasoned organic chemist to go ask somebody for a second opinion on a name sometimes if it's a complicated molecule. So the next section kind of deals with a little bit of comparison of addition versus elimination. So remember, elimination, that was chapter 7. Okay, and we looked at two types of eliminations, E2 and E1. Most of the time we looked at E2, but because it's a lot more common. But in chapter 8, this is where we're going to be talking about addition. So if you're wondering, what's the difference between the two? When is one favored over the other? How come sometimes I get elimination, sometimes I get addition? Well, that's kind of what this section is about, okay? So just follow along with me and you'll get it, no problem, okay? It says addition and elimination are in equilibrium with each other, right? Remember equilibrium, right? We use equilibrium arrows. And then it says which side is favored actually depends on the temperature. So you can actually control whether you get elimination or addition based on temperature, and that's what we're going to cover right now. And so it says here that the higher the temperature, the more important entropy becomes. And that's just something that this is more like a bullet point that you know this already. You've heard this so many times, but it's just kind of a review. If you've forgotten, okay, remember, when a reaction is spontaneous in the forward direction, that's when delta G is negative. And so we look at the enthalpy term and the entropy term. All this statement is saying is the entropy term is the second term, okay? The bigger that T is, right, because T is in Kelvin, it's always a positive number. The bigger the temperature is, the more entropy is going to be important, right? The higher the temperature, the more entropy starts to come into play. If you do the reaction at a really super low temperature, then entropy has less of an effect, okay? So that's all it's saying, and that's why temperature is going to be the deciding factor as to whether we get addition or elimination. So what we've got to do now is we've got to look at the enthalpy term and we've got to look at the entropy term, and we'll compare the two, and that's going to give us the answer as to when is addition favored and when is elimination favored. Here we go, okay? The first thing we're going to look at is delta H. So enthalpy, delta H. What's the delta H for an addition reaction? Well, generally speaking, sigma bonds are stronger than pi bonds. And so when we do an addition reaction, what we end up breaking is we break one pi bond and one sigma bond, and then we end up forming two sigma bonds. So we formed, oops, I'm not circling the right bonds. We form two bonds that are more stable than the bonds collectively that we broke. So since our formula for delta H that I taught you in chapter 6 is this formula here, bonds broken minus bonds formed. So we covered this in chapter 6. Since the bonds formed are stronger than the bonds that are broken, we get a bigger second term, and so our delta H is negative, right? So then we know, since our formula is delta G is equal to delta H minus T delta S, we know that delta H is a negative term. Now we're going to look at T and delta S. Well, obviously T is always a positive number, but what's the change in delta S here? We're going from 2 molecules to 1 molecule. So is this a positive delta S or a negative delta S? Could anybody answer that for me? Thanks, Katana. I answered that faster than I could ask it, right? It's a negative delta S, isn't it, right? So addition reactions, what we cover, again, this is the whole point of chapter 8. All these reactions, they're not entropy favored, right? Delta S is a negative number because you're going from 2 to 1, right? So our delta S, we can put it here, is going to be a negative number. Entropy is not increasing when we do an addition reaction. So let's take a look. Let's put the whole kit and caboodle together. Maybe I will write it over here, okay? We're going to say delta G is equal to delta H minus T delta S. We said that delta H is a negative number. Then we're going to subtract. Now T is a positive number, and it's going to be multiplied by a negative number. So if you take a negative times a positive, you get a negative. So we have a negative, and we're subtracting overall a negative term here. Give me a thumbs up if you're with me so far. A negative, and we're subtracting a negative. So what does that mean? It means that when the temperature is low, right, you're going to get a negative delta G because you're going to have a small negative number, right? You subtract a negative, it's like you're adding something. But when the temperature is super high, then the negative number is going to be really big, and it's like you're adding a number that's going to make the delta G positive, okay? That's all that's going on here. And so based off of that, at low temperatures, the enthalpy term, or the delta H, is going to be the major player, and the addition reaction is going to be favored, right? Because delta G is going to be negative. But if you jack the temperature up enough, then entropy is going to be the dominant term, or the second term is going to dominate, and you actually end up with a delta G that is positive. Delta G is positive, and so elimination reactions are favored. Now, I might ask you some questions about this on the homework. I don't think I've ever gone into tons of detail about this on a quiz. Probably a little bit, but this is the crux of what you need to know. It's shown down here, right? You need to understand that at low temperature, addition is going to be favored. So this is chapter 8, our chapter that we're dealing with right now. And chapter 7, that was, remember we heated something up to make an alkene? Yeah, okay? So that's why. It's based off of that entropy term. Give me a thumbs up if you're with me 85% of the way on this, or if you have a question, stop me. It's just an important thing for you to understand before we move on. All right, cool. So what are we going to be seeing in this chapter? Lower temperatures usually in chapter 8. Okay, we're not going to be heating things up sky high or anything like that. So you ready? Here we go. We're on slide, what does it say? Slide 18 of 119. Well, this is where we get into the reactions, right? Remember I told you we looked at all these different addition reactions that were covered on that, what I call the wheel of reactions, so to speak. So this is the first addition reaction that you're going to learn in this chapter, and we're going to learn several of them. But let's get started here. The first one is hydrohalogenation. It's the addition of a hydrogen and a halogen to an alkene. So how do we get a hydrogen and a halogen? We get it from HCl, HBr, or HI, either one of those molecules, not HF. Okay, we don't do this reaction with HF. And the reason why is HF is not a strong acid, so it doesn't work. And you see that we're at low temperature when we do this addition reaction, right? So our enthalpy term is going to dominate. And you see we actually get a pretty good yield, 76%. This is actually not that bad. So what do is that you have the HBr molecule, okay? What are you adding? You're adding a hydrogen atom. So here's the hydrogen. That's this hydrogen. You added it here. And then you added the bromine atom, and that is added over here. There you go. Give me a thumbs up if you're with me on that. You add the hydrogen to one of the sp2 hybridized carbons and the bromine to the other sp2 hybridized carbon. Now we're going to get into the mechanism of all this in just a second. But what I'm going to cover in the next few minutes is we're going to study the two possible regioisomers you can get when you have an asymmetrical alkene. Okay, so what if you have an alkene like this one down here that is not symmetrical? You have two different vinylic positions. You see that one of them has a hydrogen attached to it and the other one has no hydrogens attached to it. And really what we're going to get into now is something called Markovnikov's rule. Markovnikov's rule, or Markovnikov addition, okay? This is one of the major rules that you're going to learn in organic chemistry. If you have a cousin or a sister, brother, well-wisher, friend, somebody who's taken this class before, and you ask them, do you remember Markovnikov's rule? They might not remember the rule, but they'll remember the name, okay, for sure, because it's covered so extensively in any organic chemistry class. So the rule is this. The rule is nothing more than this. We'll put it here. The rich get richer. Okay, that's kind of the way my students remember it. So what I'm saying is this: if you have an asymmetrical alkene like this one, you see how this carbon that I have highlighted in red has one hydrogen on it? Everybody with me on that? That carbon in red has one hydrogen on it. The other carbon, I'll put it in blue, has no hydrogens on it. So here's the answer. Whichever carbon is richer in hydrogens, it's the one that takes the hydrogen. The other carbon takes the other group. So if this was HX, the major product, or what we call the Markovnikov product, would be this, where this carbon takes the hydrogen, okay, and the other carbon takes the X. This is what we call the Markovnikov product, Markovnikov product, and it would be the major product. If you have the other regioisomer where you switch the hydrogen and the halogen, we call that the anti-Markovnikov product. And there's ways to obtain that product too. And if you're wondering, is there some kind of rationale for this? Yeah, there definitely is. And I'm going to go into it in detail. So regioselectivity. Hydrohalogenation is regioselective for that rich getting richer, the Markovnikov addition product. And you can see that organic chemists have known this for a long time. And Markovnikov, I think he was a man of many interests. You know, I think he was an organic chemist and a lawyer and like a shoe repairman or something like that. I think he could fix your shoes and, you know, draft your will and do some experiments for you all in the same afternoon. Anyhow, very interesting guy. So he discovered that he kept trying this reaction over and over and over, and he kept noticing that the carbon that was richer in hydrogens is the one that kept taking, right, kept taking the hydrogen, that kept taking the hydrogen from the hydrohalide, right, from HBr, HCl, or HI. Okay, so it says here, again, Markovnikov's rule is that the halogen generally goes to the more substituted carbon, or you can think about it as the rich getting richer, right? Whichever carbon is richer in hydrogens gets the hydrogen. Give me a thumbs up if you're with me on Markovnikov's rule before I get into the rationale of it. Just the remembering the rich get richer. And this is just another way of presenting it. Whichever carbon is more substituted, that's the one that takes the halogen. I don't care which way you remember it, but my students never forget the rich get richer. They always remember that. All right. So now, Markovnikov did this way back in the 1800s. So he didn't have a lot of fancy equipment to work with. And he noticed that sometimes he would do the reaction and he got the opposite regioselectivity. We call that the anti-Markovnikov product. You'll see me abbreviate it as anti-Mark because I get tired of writing Ovnikov all the time. But anyhow, he noticed that oftentimes he got the anti-Markovnikov product in a high yield. And let me tell you, there's a lot of, I should say, not funny, amusing history about this, where Markovnikov was scratching his head. He could not figure it out. Why is it sometimes he was getting Markovnikov, other times he was getting anti-Markovnikov? And I mean, keep in mind, this is the 1800s, okay? They proposed all kinds of stuff. They even thought it might have had something to do with the phases of the moon, okay? They said, oh man, why is this happening? And you know what he figured out? He figured out that if he purified the solvents, he always got the Markovnikov product. But if he used older solvents that hadn't been purified, he got the anti-Markovnikov product. And so what he was getting in the impure solvents was this, is a peroxide. And that's very common for organic solvents. If you leave them out long enough and you don't purify them, that they get peroxides just building up in them over time from exposure to oxygen and sunlight or electromagnetic radiation. And so if he put peroxides in the solvent, he got anti-Markovnikov, but if it had no peroxides, he got the Markovnikov product. And so the two mechanisms are completely different. And in fact, the mechanism of this reaction, I'll put here mechanism of this is not covered till the very end of this class. It's covered in chapter 10, the very end of Organic Chemistry 1. However, this reaction, okay, this one here, the one where you don't have peroxides and you get the Markovnikov product, oh, you bet your bobby socks I'm going to cover this with you in Organic Chemistry 1. Super important. Now, before we get into that, let's just take a look here. So what's the conclusion that Markovnikov came to, okay? He came to this conclusion that if he had a pure solvent and he just took HBr and treated it to an asymmetric alkene, he got the Markovnikov product, right? The rich getting richer. Again, to review, this carbon has two hydrogens attached to it. Okay, so now it's got 1, 2, 3, and the third one came from the HBr molecule, okay? And then, or you could look at it as the most substituted carbon, which is this carbon, takes the bromine atom, and there it is right there. Okay, so that's Markovnikov. But if you used impure solvents, where he had peroxides, and if you're wondering about the structure of it, you're like, what's ROOR? So it's just the formula for peroxide. And students will sometimes ask me, could it be hydrogen peroxide? That's H2O2. The answer is no. It has to be an R group. It has to be an organic peroxide. And when we get into chapter 10, I'll cover more detail of what the R groups can be. But for now, don't worry about it. Just worry about this. If you write H2O2, that is a big time, that's a big no-no. Okay, that would be a huge no-no, so don't put hydrogen peroxide there. All right, let's keep going from there. And it says here, so let's try a little practice problem, okay? So if I take this cycloalkene, so this would be 1-cyclopentene, is what you would call this compound. So this is 1-cyclopentene, right? Cyclopentene, you've got this, which is cyclopentane. You put a double bond, it becomes cyclopentene. So if you put a methyl group here, it's 1-cyclopentene. All right, so if we add HBr to that, I'm going to highlight this carbon in red and this carbon in blue. Could anybody tell me which one of these carbons is going to take the hydrogen atom? Blue or red? Exactly, it's the blue one because it's richer in hydrogens, right? It has one hydrogen attached to it. The carbon in red has no hydrogens on it. And so our final product is going to be this. Okay, we're going to have this will be our final product. Now, if you wrote this, if you just said, well, I wrote everything in there, I put the bromine and I put the hydrogen here, you can do that, okay? But it's kind of a weird way of drawing it because you're missing a hydrogen here if you didn't put two there. And then you're kind of mixing like condensed structures and Lewis structures at the same time. So I'm not a big fan of doing that, so I'm going to try to avoid doing that with you. Okay, let's try the same thing over here. If I put this carbon in red and this carbon in blue, now it's going to be anti-Markovnikov addition. Which carbon is going to take the proton, the one in red or the one in blue? If it's anti-Markovnikov. Yeah, it's the one in red. Thanks, Hannah. Absolutely. And so we're going to end up with this compound. We get something that looks like this. There we go. So again, this is going to be Markovnikov, and this is going to be anti-Markovnikov. There you go. Markovnikov and anti-Markovnikov addition. Super important term. Now what I want to cover with you is the mechanism and why is it that we end up getting the Markovnikov product and not the anti-Markovnikov product. You know what I'm going to do, though, is I'm just going to switch over to a blank document here and kind of go over it with you here, just out of my head, okay? So let's think about if we had an asymmetrical alkene like this, right? This carbon has one hydrogen attached to it. The other carbon has no hydrogen. So if we want to do the addition of HBr, okay, and again, we could do the same thing with HCl, but we'll just pick HBr today, okay? So what's going to happen is the rich are going to get richer. So this carbon is going to take the hydrogen from HBr, okay? So my double bond is going to act like a base, right? And it's going to grab this proton. We're going to break the bond between the hydrogen and the bromine. And here's what we're going to end up with. We're going to end up with something that looks like this. The proton in red is there. Maybe I should put it in red, but anyhow, there we go. And we end up with this proton in black. I'll circle it in green, just so you're sure that it's this proton here. Now, this carbon is a carbocation. All right, everybody with me on that? Just protonation of the double bond and making a carbocation. Any questions about that? No? Okay, so now look, if we did it anti-Markovnikov, so let me just copy this, okay? So I'll copy this and I'll paste it down here and we'll compare the two. Okay, so let me just delete these arrows. And now what we're going to do, so again, this is Markovnikov addition, and I haven't finished the mechanism, right? I just drew the carbocation. Now, if we do anti-Markovnikov, what's going to happen is we're going to grab, I'll use blue curved arrows this time, is that this carbon is going to take the proton like this, and I'm going to end up with something that looks like this. So now I've got my red proton here still. I've taken this proton from HBr, so I'll circle it in blue. Or no, I'll circle it in green, I guess, since it's already circled in green, like that. And now I have my carbocation over here. So now what I want you to do is I want you to compare these two carbocations that I have here. Which one of these carbocations is more stable, the one on the top or the one on the bottom? The one on the top, right? Thanks, Kiana. Yes, the one on the top is going to be more stable. Could anybody tell me why? Go with your gut. Probably going to be right. Why is the one on the top more stable than the one on the bottom? Exactly. So my students nailed it, right? Everybody said this is a tertiary carbocation and this is a secondary carbocation. All right. So there's the answer. Okay. That is the entire answer as to why Markovnikov addition is preferred. It's because the activation energy of the first step of the addition of the proton is going to be lower than if you do anti-Markovnikov. Why? Because you get a more stable intermediate. There's the answer. That's the whole entire thing. Now, if you're wondering, why don't you finish the mechanism? Well, I will. Okay. But the second step, all it is that bromide is going to come in as a nucleophile and attack the carbocation, or just, it's going to attack the carbocation, and that's the end. So we get, oops, where's my black pen? No, I'll use my red pen. Here we go. You get a nucleophilic attack here, whoop, over here, and that gives you the two products. So in the case of Markovnikov addition, you end up with this compound, and in the case of anti-Markovnikov addition, you get this compound. But of course, you need HBr and peroxides, right? For anti-Mark, you need peroxides to get it to work. But I'm going to go over the slides with you now, which basically explain this. But this is the whole explanation, really everything you need to know. This is Markovnikov versus anti-Markovnikov addition. That's the whole kit and caboodle right there. All right, so let's go back to our slide deck. Find it. Where is it? Somewhere around here. There we go. So where we were somewhere around here, and we were looking at Markovnikov and anti-Markovnikov. We tried a little practice problem here, and that's the mechanism as drawn by David Klein himself, okay? So the mechanism is two steps. The first step is the proton transfer. Of course, it's the rich getting richer, so that's what's happening here. Rich getting richer. The one that's richest in protons, which is this one, is the one taking the second proton. Okay, then you get a nucleophilic attack and you're done. And again, the graphical interpretation is this here. The activation energy to form the tertiary carbocation, this activation energy is going to be lower than the activation energy to form a secondary carbocation. And there you go. So there's the anti-Markovnikov pathway, the exact same way that I drew it. And here's a comparison of the first step for the two of them. And you just see that when you form a tertiary carbocation, this is the whole answer right here. The activation energy is lower. Nothing more to it than that. Give me a thumbs up if you're with me on that. Even if you're with me like 70% of the way and you're like, yeah, I follow you most of the way. I'm going to go back and look at it myself. Sure. Okay. Can I ask you a question then? If we go back here and we look at a carbocation like this one here, and this is just me quizzing you, could anybody tell me what's the hybridization of a carbocation? Let's just review. What's the hybridization of this carbon? It's a carbocation. Going to be sp something. Hybridization of a carbocation is sp2. Okay, so if it's sp2, what's the molecular geometry of a carbocation? The molecular geometry is trigonal planar. Yes, thanks, Sean. It's trigonal planar. And if it's planar, that means it's flat. So the idea is this, is that when your bromide comes in, just erase this here. So when the bromide acts as a nucleophile, Sean, it can attack from the front face of the molecule, or it can attack from the back face of the molecule. And so the idea is that if you form a chiral center, you end up with a pair of stereocenters, right? So where is it? Right here. So hydrohalogenation, if you get a chiral center, you're going to get two enantiomers. If you form one chiral center, you're going to get a 50-50 mixture. Give me a thumbs up if that makes sense. If you want an explanation in more detail, they've drawn it right here. He just says you've got your sp2 hybridized. This is your carbocation. It's sp2. It's trigonal planar. That means it's flat. So that means the nucleophile can come in from the top face or the bottom face. It's indiscriminate. And so you get a racemic mixture. And that's all there is to it. But that's something you have to know. It's going to be important in the homework. It's going to be important in quizzes and everything. And if you're really astute, and I know you all are, and you're thinking, now hold on, Mr. Dion, you showed me a carbocation in that reaction. You told me that when a carbocation rearrangement can occur, it will. The answer is yeah, it can. And so we have to take carbocation rearrangements into account when we're looking at Markovnikov and Markovnikov addition as well. We don't look at the mechanism of anti-Markovnikov. I kind of let that slip out of my mouth. And so if you had a compound like this one here, okay, so this is what, 3-methyl-1-butene. So this is 3-methyl-1-butene, okay? You form that secondary carbocation, but it can undergo a hydride shift to give you a tertiary. And so, yeah, it can definitely happen. And so what happens in that case is when a carbocation rearrangement can happen, it will, and you usually get a mixture. So you get a mixture of both the rearrangement product and the non-rearranged product. And if you're sitting there rolling your eyes going, oh man, more products I need to know, the answer is absolutely, okay? It's just it's par for the course, okay? It's something that we have to master. And so let's get some practice on this. This is question 8.5 from our textbook. Oh, sorry, I think is this 8.5? I think this might be 8.8. Let me just double check to make sure I have my numbers right. Sometimes I'll mix stuff up here. So this is, oh, I forget. I think I had, does anybody know? I'm going to be posting this to YouTube, me asking my students, which question is this? I thought it was 8.8 in the new edition. No, it's 8.5. No. Let me see here. It's 8. Anyhow, the number's not important. The question is here. Somebody said it's 8.9. Is that what it is? 8.9? You guys are probably right. I just want to double check. There, you're right. It's question 8.9. Sorry, my mistake. This is question 8.9. I knew it wasn't 8.5 in the new edition. There we go, 8.9. Thank you so much for helping me out on that. That gave you some time to think about it, right? Okay, so let's take a look here. It says predict the products of each of the reactions. In some cases, the reaction produces a new chiral center. In other cases, no new chiral center is formed. It doesn't ask us to draw a mechanism, but it's kind of fun to try. Let's practice a little bit here. So we're taking an alkene, we're treating it with HBr. What's going to be our major product? Or our only product, I guess. Is it going to be Markovnikov or anti-Markovnikov addition in this case? It's going to be Markovnikov. Thanks, Hannah. So this is a Markovnikov addition. Yep. So the rich are going to get richer. So this carbon here is the one that's going to take the proton, and I'm going to end up with a carbocation. I'm just going to draw the carbocation for interest's sake here. So we end up with a tertiary carbocation. And now my bromide can come in as my nucleophile, and it can attack from the back face of the molecule, or it can attack from the front face of the molecule. It doesn't matter. And so we're going to get a pair of enantiomers, right? Because we're going to have one chiral center, aren't we? So we're going to end up with this compound. We have the bromine coming out and the methyl group going back. And then we're also going to have this compound where we have the methyl group out here and we have the bromine in the back, okay? So these two compounds are enantiomers. I don't know how that turned red that quickly, but anyhow, give me a thumbs up if you're with me on that one. Any questions on this one? No? Okay, well, in the second one, do we form a chiral center? The second one, do we form a chiral center? Right, if I highlight this carbon in yellow And this carbon in green, which one of those two carbons is going to take the chlorine? The yellow one or the green one? Which one will take the chlorine? Well, it's going to be, right, because this is Markovnikov addition. Right, so the chlorine ends up on the more substituted carbon. Yes. And so if we draw the product, we have something that looks like this. We're going to have a methyl group here and a chlorine here. Right, so there's no chiral center in here. Yeah, there's no chiral center, right? You've got a propyl group here and a propyl group here. So this is an achiral molecule, so achiral. And then in the next one, are we going to form a chiral center in the next one? Could anybody answer that? Well, let's draw it, okay? So if I highlight this carbon in green and this carbon in red, which one of those carbons is going to take the iodine? The green one, right? So if we draw that, we end up with a chiral center, don't we? So if we draw that, we have our two methyl groups here. Then we're going to have one enantiomer. There'll be the methyl group in the back, the iodide in the front, and then we're going to have the other enantiomer where that chiral center is reversed. So we're going to have the iodide in the back and the methyl group coming out like that. And so we get a pair of enantiomers. All right, let's move on from there. And let's take a look at what are the reagents you would need to achieve each of the following reactions. So the first reaction is a hydrohalogenation. So we're going to need HBr. Is this a Markovnikov addition or an anti-Markovnikov addition? What kind of, is this a Markovnikov or anti, right? No, this one is Markovnikov, right? The rich are getting richer. This carbon has 2 hydrogens. Now it has 1, 2, 3 hydrogens, right? So the rich are getting richer. So this is a Markovnikov addition. So we only need HBr for this one. All right, does that make sense now? Okay, so again, I'll draw it out again. So this carbon has 1, 2 hydrogens, and then when the reaction's done, it's got 1, 2, 3, right? Another way you can think of it is this carbon is the most substituted and it takes the bromine. So it's Markovnikov addition. The other reaction, right, the second one, we're going to need HBr because you're adding HBr to the molecule, but is this Markovnikov or anti-Markovnikov? This one is anti-Markovnikov, so anti-Markovnikov. And so we need HBr and an organic peroxide. And there you have it, folks. All right. So that brings us to section 8.6, which is our second addition reaction. So far, we've covered the addition of HBr, maybe I should use green, either HCl or HBr, or HI would react in the same way. And now we're going to look at the addition of H2O, okay? And this is an acid catalyzed reaction, the addition of water across a double bond. You guys want to take a quick break first, though? I think that might be pertinent before we get into this new section.